Good morning, and thank you for the invitation to speak here. And I welcome you to my presentation about synthesis of 7-DSH, a natural sugar from cyanobacteria on its way to a sustainable herbicide as an alternative to glyphosate. So why do we need a sustainable herbicide? So we are using more than 800,000 tons of glyphosate per year, mainly in agriculture. And the global glyphosate market has a value of 9 billion euros with a market share of 90%. But glyphosate has a negative impact on the environment, on insects and humans, as you probably know. And it's hopefully going to be prohibited in the European Union until the end of this year. So we really urgently need an ecological acceptable alternative. This could be 7-desoxysedoheptulose, in short 7-DSH, which is a novel herbicidal candidate. The first toxicology tests are promising, showing that it's less toxic than glyphosate. And this sugar was isolated from culture supernatants of Synechococcus elongatus, but this cyanobacterium produces very low amounts, primarily in the stationary phase of cultivation. So currently in use is an in vitro chemoenzymatic synthesis of 7-DSH, but it has a very low yield of 20%. The substrate costs are quite high, and therefore this process is not economically feasible. But fortunately, we have an alternative production strain, which is Streptomyces cetonensis. So it's as well a natural producer. It's secreting 7-DSH to the media. Other Streptomyces strains are already established in industries for the production of antibiotics, and we can use various feed sources. Of course, there are also some drawbacks, which is that the titer of 7-DSH produced is only 23 milligrams per liter, and it's unknown if degradation occurs. The growth rate is unknown, as well as the synthesis pathway. And as you can see here on the picture, it grows as pellets. So this makes OD measurement impossible. But now we already have a starting point for a bioprocess, which brings me to the project overview. So my part of the project is the development of a bioprocess with Streptomyces cetonensis for the large-scale production of 7-DSH. And also to some extent the purification, and afterwards the part of my colleague is the formulation of 7-DSH so that it's an applicable herbicide for agricultural fields. You can also see my poster for that part. So how can we evolve a scalable, well-characterized bioprocess for an unknown microbial system? I've chosen to firstly investigate the media composition and process parameters with a design of experiments approach. So for that, I've chosen basic parameters as the pH, the osmolarity, and macronutrients, namely the carbon and nitrogen source concentration. Also, I've decided to investigate the parameters filling volume and shaking speed, because these two parameters influence the oxygen availability and the shear stress. So here you can see the results from the best approach of the DOE. It produced around 2 grams per liter, which means that the production is already increased by factor 100. So the parameters I've identified as being beneficial for growth and production is elevated osmolarity, higher glucose concentration, and lower speed. And the parameter lower volume was only beneficial for the production, which means the oxygen of the culture could have an influence on the production, because lower volume means we have more oxygen in the culture. So if you're interested in the results in detail, please also see my poster number 66. So maybe you've noticed that one macronutrient was missing. So this is phosphate. And phosphate is known as a trigger for the production of secondary metabolites in Streptomyces. So that's why I've chosen different phosphate concentrations to be investigated with a high throughput microbioreactor, namely a bioreactor. And here you can see the results. So I've measured glucose concentration in gray and yellow after 7 and 10 days, and also 7-DSA concentration in orange and blue after 7 and 10 days, with various phosphate concentrations. So what we can see is that if we have lower phosphate, reduced by factor 0.5 compared to the standard medium, that the glucose is not depleted completely. So we end up with 7 to 9 grams per liter, which means we really have a limitation in this cultivation. But if we take a look at the 7-DSA concentration, it's not so high. So it's lower than for the treatments with higher phosphate concentrations. And we can also see that for higher phosphate concentrations, we still have some glucose after 7 days, but after 10 days, the glucose is almost consumed completely. So what we can conclude is that the higher phosphate concentration is beneficial for the 7-DSA production. So let's come back to the oxygen influence I explained earlier. I measured the oxygen transfer rate, in short OTR, with a respiratory activity monitoring system. And the OTR stands for the oxygen consumption of the culture. So therefore, we can see the metabolic activity of the organism in culture. So what we first can see here is that the organism is not oxygen limited, because it just goes, the OTR just goes up. So this is good to know that there's no limitation of oxygen in my cultivation. And then, so here you can see the conditions in the minimal media. And because the phosphate concentration also has an influence on the osmolarity, I decided to have a same start osmolarity of 0.6 with very natrium chloride concentrations. So here you can see the OTR curves. So if we have less phosphate in the treatments, which is shown in green and blue, then we can see that we here have an earlier change of the growth rate. So here it's still going up, and here it's like not that much going up anymore. And we also see that the maximum OTR is reached later. So for these and these treatments a bit earlier. What we can also see, and it's really interesting, for the higher phosphate concentrations shown in gray and yellow, so these two, we reach a plateau in the OTR after the maximum OTR has been reached. At the same time, for the treatments with lower phosphate, we see that there is a steep decline in the OTR. And what is interesting, to this time, the 7-DSA production starts. So with almost the same rate, except for the treatment with the lowest phosphate concentration, where we also only reach half of the 7-DSH titer. And another point which is interesting is we have another plateau in the OTR here in the end of the cultivation for the higher phosphate concentration, which might be due to 7-DSH degradation. So let's take a closer look at the point of metabolic change, which is happening here after the maximum OTR. So here you can also see the glucose concentration, and there's still glucose left at this time point, around 3 to 4 grams per liter. And then the glucose is consumed with a comparable rate. But so the glucose is not the reason for the metabolic change at this point. So we can conclude that elevated phosphate is beneficial for the production, and the aim is now to keep the cells in this metabolic state, which is reached after the maximum OTR. So in the end, I would like to show you the effect the 7-DSH, which I produced, has on plants. So on the right side, you can see the control experiment where only minimal media was added to the agar plate where the plant seedlings are growing. And this experiment was kindly conducted by my project partners in Tübingen, who also provided the pictures. So the plant here is developing, getting roots, getting leaves, it's growing. And on the left side, you can see if 7-DSH, which is from my culture supernatant, and only filtered, not further treated, added to the media for the plant seedlings are not growing. So that's what we want to see from a herbicide. So to conclude and give you an outlook, I've increased the production by factor 100 from milligrams per liter to grams per liter. And I've identified an elevated osmolarity and higher phosphate concentration to be beneficial for the 7-DSH production. And I realized that phosphate limitation is not a trigger. So the search for the trigger of the production is still ongoing. But I've seen there's a metabolic change after the maximum oxygen transfer rate has been reached. But there's still glucose, so the substrate left in the media. So the question is now how to keep the cells in this state. For this, I would like to do a scale up into a 2-liter bioreactor, investigate the operation regime, so repeated batch and fed batch, and also do a cell immobilization, compare a stir tank with a fixed bed reactor. And also I would like to try to make the strain growing dispersed instead of in pellets. So thank you very much for your attention.